So the section 1.5 is dealing with linear equations, and you all should feel pretty comfortable with linear equations. I'll do a few examples. I'll do a simple one, and then I'll do a messy one, give you a bunch of warnings. We'll do a few word problems, and so forth. So let me just start you off with an example. My printer didn't work today, so I have to do this. So 3 times x minus 5 plus 6x equals negative 11 times 2x minus 3 plus 1. So this is a very simple, friendly linear equation. How would we go about solving it? Yeah, distributive properties, so run 3. So that's 3x minus 15 plus 6x equals, do the same thing, negative 22x plus 33 plus 1. Yeah? Now what? Combine like terms. 9x minus 15 equals negative 22x plus 34. Now what? Add 15 to both sides. So it cancels on one side. At the same time, add 22x to both sides. So that gives you 31x equals 49. Is that close enough? Right? And finally, do what? Yeah, divide by 31. So x equals 49 over 31. Not much to it. So we got the solution to be 49 over 31. What does it mean that the solution is 49 over 31? What does it mean that we have this solution? What does this number do? No, it's actually just a point. As far as we're concerned, it's a kind of a one-dimensional thing. So it's just a point. But what does that point do? What is this value? Oh, yeah. So it's a solution. So it means if I substitute it back into the original equation, it makes it balance. Very good, right? Keep that in mind. That's what it means to solve equation. You want your original equation to balance. So having said that, I have another equation, if I can get to it. All right, so here's a fun one. And this is maybe a little bit advanced for linear equations. It doesn't look like a linear equation at the moment, but we can still solve this thing. And there's one little trick that I'm going to teach you. And this trick will kind of stay with you for a while. Because, well, what makes this equation potentially difficult? Yeah, denominators, just different denominators, just denominators period. Every time you see fractions, even numerical fractions, it'll make your equation a little messier than it should be. But we understand one thing is that if I multiply one side of the equation by something, I'll have to multiply the other side of the equation by the same quantity. So we can actually get a little sneaky here. If I take a look at each denominator that I see here, and I ask you, what is the least common denominator for all expressions here? What would that be? What? Just 2? What about all those x's? So I need x minus 2. It's one of the factors. Do I need x plus 2? Yeah, it's a totally different factor. Now, do I need x squared minus 4? No, because that is x squared minus 4. right? So my question to you is, can I just go ahead and multiply the left side of this equation by x minus 2x plus 2, and can I multiply the right side of this equation by x minus 2x plus 2? Is that legal? Yeah, when I multiply on one side, I do the other. So now think about this. On the right side, since x squared minus 4 is the same as x minus 2x plus 2, it's just going to cancel out. Because I'm multiplying and dividing by the same quantity. So the right side is identically 4. Is that okay? Well, now I'm going to distribute through the parentheses. I know it's hard to see, but what I'm doing is I'm multiplying by x minus 2, x plus 2, and then I'm dividing by x minus 2. Is something going to cancel? X minus 2 will cancel because I'm multiplying and dividing by the same term. What is going to be left if x minus 2 cancels? X plus 2 times whatever that is, so just x plus 2 times 1, so it's x plus 2. And then we'll do it again. We'll distribute it through. What's going to cancel on that second product? X plus 2. And then we're left with negative 3 times x minus 2. Right? So all denominators canceled in one move. So that's a little trick. You'll see this trick again, but just keep this in mind. If you have an equation that contains fractions, any type of fraction, you can always do this. You can always multiply both sides by the least common denominator to clear out all the fractions. It'll make your problem a whole lot easier, because look how nice this question is. Isn't it nice? I mean, look at this. In one move. Now, the rest is kind of what we just did. It's a linear equation. Distribute 3, blah, blah, blah. So what is this? Negative 2x plus 8 equals 4. When you combine like terms, subtract 8 from both sides, gives me negative 2x equals negative 4. So finally, x equals 2. Is that okay? So what does that mean that we just found x equals 2? What is x equals 2? A point? What kind of point? What is so special about x equals 2 right now? Kind of going back to my previous question about 39, 40, whatever. What does that point do? So if I take it back to the original equation, it should balance it. Now, does it? Does it actually work if I take x equals 2 back into my original equation? What happens if x equals 2 in my original equation? Is that a good number to plug in for x? No, why not? Yeah, my first fraction turns into 0 in the denominator, so that's undefined. So x equals 2 is not even in the domain of all those functions. So whatever solution we found does not work when we substitute it back in. So what does that tell you about the solutions to this equation? If the only, no solutions. This one is turns denominators into 0. So no solution. So this is the only thing you have to be careful with. When we do problems like that, when we cancel out denominators in this fashion, just make sure that denominators don't turn into 0 when you substitute your answer in. Because it's really easy to fall for that. You'll see later on your MML homework, solve this equation, and you get like 5, 4, and 3, but 3 doesn't work because of the denominators, and you list your answers as 5, 4, and 3, and I'll just mark you wrong. Because only like 5 and 4 work. That makes sense? So we have to be careful with the denominators. Is that okay? All right. Now, a little extra verbiage. How do you spell verbiage? Is that even a word? Yeah. So that's how we're going to spell it, since we're inventing words now. we want to introduce a notion of a zero of a function. Okay, so we're just gonna, the book tosses this definition at us kind of early, so I'm going to define it. I'll explain what it is. It's a pretty straightforward concept, and you'll probably have questions where you have to find zeros. So zero of a function. So here's the definition. X equals C is a zero of a function if f of C equals 0. Very simple definition. Whatever number turns your function into 0 is called zero of a function. C itself does not have to be 0. C could be anything. But as long as it turns your function into 0. Actually, it's a two-way street. I should have said x equals C is a zero function if and only if. Do you know the difference between if and only if and just if? What? Well, it means it works both ways. Because if I just say if, then that works. It doesn't mean it has to work backwards. Think, if it's raining, then there are clouds in the sky. How do you like that statement? Is that, is that okay? If I reverse it, is that true? If there are clouds in the sky, then it's raining. So, but this one works both ways. So when we want to do that two-way street, we usually say if and only if. That's a two-way street. And we're very lazy. Remember in math, we like to abbreviate a lot. We don't write if and only if. We write double F if, like that. If. That means if and only if. So every time you see an if with two F's, that's a two-way thing. So, but the concept is really simple. For example, if I ask you find zeros of the function, and I give you something like this, f of x equals x plus 1, so you have to find all x value that turn your function into 0, which in this case is what? What is the 0 of this function? -1, and that's it. So that's what we mean by zeros of the function. Whatever turns the function into 0. So the zeros, x equals -1. So you're really solving an equation. Your function equals 0, and you solve for x. Okay. Is that okay? Just a little definition, you'll see it. Because this section is kind of weird, this end of the chapter. Gives us different ideas, because you'll use linear equations to solve for that eventually. And finally, in that section, we want to talk about interest, computing interest. And we will see 3 different formulas for computing interest in this course. 2 of them will come later in chapter 5, but the first one is called simple interest. And it basically says that in order to compute the interest of an investment or money borrowed, whatever, you have to perform the following operation. It's P, which is the principal, the amount borrowed or amount investment. It's principal. Is it a principal like this, or is it a principal like? No, it's like that. Right? Principal is the guy who works at the school, right? He's a pal. So principal times rate times time. So PRT. Now, rate and time should be measured in the same units of time. So if it's an annual rate, then time should be measured in years. Okay? So we'll see things like that. So let's do a few examples. We're going to pull problems out of your book. And I had few I wanted to do. So 46. And we kind of played with commission, I think, earlier. So section 1.5. Oh, I could have just done it from here. Section. All right. So I want us to do this problem. All right. Can you see the story? Oh, yeah? I'm getting all high-tech when you're there. It's going to be part of your notes, too. Does the story make sense? She has two choices, either $1,800 or $1,600 plus 4% commission. Okay? So the question is, what sales should be in order for both choices to be equal? So choice one is just $1,800 no matter what, right? That's fixed. While choice two, it's $1,600 plus 4% of her sales. So how do we express that mathematically? 4% commission of the amount of furniture she sells. We need a variable, right? So what should that variable represent? What? What is x in this case? No, 0.04 is 0.04. Well, but then we can just kind of think about this. We are just lumping it all together. It's not the number of pieces that she sells, but just the amount of her sales. Does that make sense? She's, doesn't matter whether she sells 20,000 chairs or one fancy couch, whatever the total sum is. So X would be the total sales, right? What? Oh, I don't know yet. I'm not close to answering that question. But I'm just trying to express her second choice. So it's 1,600 plus 4% of whatever she sells, right? So that's 0.04 times X. That's how we compute 4% of the amount, right? So the question is, what are these two things equal? So that should be pretty straightforward. We just set them equal to each other. So it's 1,800 equals 1,600 plus 0.04 X, right? Well, that's a simple equation to solve. We'll just subtract 600 from both sides. Leaves us with 200 equals 0.04x. So then just divide. So x equals whatever 200 divided by 0.04. What is it? 5,000, something like that? Yeah. So we're done. So if she sells, but basically if we were allowed inequalities, she'll have to sell more than $5,000 for choice 2 to be better option. Or if she sells less than $5,000, choice 1 is a better option. Agree with that? So then you can make a prediction what they usually sell, blah, blah, or maybe try a little harder. I don't know. That doesn't matter. I'm not going to get into the management techniques. But that's about it. So we kind of use that simple interest formula. It's not really an interest formula per se, if you just understand how percentages work, you should be able to compute percentage of an amount. All right. Questions on this? Does that make sense? Let's try another one. The question I want to do now is, yeah, the student loan question. Well, sometimes it copies with weird lines, but hey, that's okay. Does the story make sense? I'm not asking you how to solve it yet, but just like the situation. So what do we know? He has two loans that both total to $9,000. One is borrowed at 5% simple interest, one is borrowed at 6% simple interest, and at the end of the year, his total interest is that much. That's total for both loans. Okay? So the question is, how much was borrowed at each percentage, whatever points? Okay? So we need to, let's split them up. Let's talk about loan 1 and loan 2. So let's say the rate for loan 1 is 5% or 0.05, and the rate for loan 2, well, is 6% or 0.06. Is that okay? So that's easy. The time is also easy. In both cases, just 1 year, so that's good. The only thing that's a little messy is the principal. So that's what we're going to introduce a variable, probably, because we don't know how much was borrowed at each rate. So let's say that principal for the loan 1 was X. X dollars borrowed at 5%. Okay. Now, keep in mind, we're going to end up with a nice, pretty linear equation, and we like our linear equations to just have one variable. Then that produces a one pretty solution most of the time. So I should still express principal for loan 2 in terms of X as well. Right? I shouldn't say it's Y and then be stuck with two variables. I should say it's something else. Now, how would I express the amount borrowed at 6% given that amount borrowed at 5% is X? Oh, but that's a different X. Okay, I want it to be this same X, so I don't have multiple variables floating around. Let me ask you this question. If Dmitry borrowed $3,000 at 5%, how much did he borrow at 6%? If he borrowed 3,000 here, hypothetically speaking. 6,000, how do you know that? Or, in general, 9,000 minus X, whatever that amount is. Then you subtract from 9,000 and you get the amount borrowed at 6%. Does that make sense? Because we know the total is 9,000. Well, then you can use the simple interest formula. Because keep in mind that if you add the interest from loan 1 plus the interest from loan 2, what is the total sum of the interests? 492. So now I can set it up. The interest from loan 1 is just 5% of X dollars borrowed for 1 year. So it's just 0.05 times X. Is that okay? You just multiply. I mean, you multiply three quantities. 1 is 1, doesn't contribute. For the second one, again, you multiply all three quantities. So that's basically 0.06 times 9,000 minus x. All equals 492. Does that make sense? So we separated the problem into two pieces. We computed the interest for each loan separately. We knew the sum was 492. So we can go ahead and solve this equation. It's a linear equation, should be easy to do. So let's try that. So it's 0.05x plus, I don't know, 540 maybe. Is that close enough? Minus 0.06x equals 492. Is that okay? So then if you combine like terms, that gives you negative 0.01x, and you subtract 540. So that looks like 48 negative. Yeah. So then you divide by 0.01, negatives cancel. So x equals 4,800. So then the answer here, 4,800 borrowed at 5%. How much was borrowed at 6%? 4,200. Because the sum is 9,000. So then 4,200 borrowed at 6%. So questions about this? Is that okay? Questions? Nice stuff. I mean, the interests don't usually being computed this kind of simple way. They're more advanced interest formulas, and otherwise it would be too easy to pay that stuff off. But there are more complex schemes to make a little more money off of your student loans, and we'll talk about them in chapter 5. Okay. So, so let's finish chapter 1. So the last section, 1.6, is dealing with linear inequalities. And that will be the end of chapter 1. So that means, I don't know what that means. What does that mean for you? So linear inequalities let me just start you off with an example. And you might have seen us already do linear inequalities, but example of linear inequality would be something like, 2x plus 1 is greater than negative 3. And the way we solve linear inequalities is just the same way as you solve linear equalities. You just want to get x by itself. So how would you go about solving this? Yeah, subtract 1. 2x is greater than negative 4. Divide by 2. So x is greater than negative 2. Right? So it's either this as your solution, it's all x's such that, or from negative 2 to infinity, using the interval notation, or if you ask to graph this, it's everything from negative 2 to infinity. Is that okay? Now, does anybody remember there are a few instances where you have to be careful when solving inequalities? Dividing by negatives or multiplying by negatives. Okay? So every time you multiply or divide by a negative number, the inequality will flip. Now, the reason for that, I don't know if we want to be writing this part down, but if I write this, 2 is less than 7. Is that a true statement? And I can go ahead and add any number to both sides. It won't change the inequality. If I go plus 10, well, 12 is still less than 17. Right? So that didn't affect the inequality. With me on that? What if I decide to, instead of adding 10, I'll subtract 10 from both sides? So what do we end up with? -8 and -3. Is the inequality stays the same? -8 is still less than -3. So adding, subtracting does not affect your inequality. Now what if I start multiplying? If I multiply by 3, we get 6 and 21. Inequality still holds true, right? Didn't affect the inequality. But if we do -3 on both sides, then we end up with -6 and -21. Well, now -6 is greater. So the inequality flips. So we need to remember that, multiplying by negatives. Now, multiplication is the same as division, so dividing by negatives. I kind of chose ugly numbers, but if I divide both by negative, well, let's just divide by negative. I don't know. What's your favorite negative number? -5, right? So we have -2/5 and -7/5. Which one is bigger? -2/5, right? It's closer to 0 from the other side. I mean, it's to the right than -7/5. So again, the inequality flips. So the only time the inequality needs to be reversed is when you multiply or divide by negative numbers. There's another instant when the inequality is reversed, and you don't see it very often. But if I, again, start with 2 less than 7, that's a true statement. We like that. But if I take reciprocals of both sides, if I flip both sides, which one is bigger now? 1/2. So that's another instant when inequality gets reversed, when you take reciprocals of both sides. Okay? All right. So we need to keep that in mind. I don't know if I should write that all down after this long speech. You want me to write it down? Add, subtract, okay. Multiply, divide by positive, okay. Multiply, divide by negative, flip the inequality. You got that? All right. I mean, you knew that before you've met me, right? I didn't teach you that. Let me just do a few examples where we do that type of stuff. All right. So 13 minus 7x is greater than or equal to 10x minus 4. So how do we go about solving this? Just like a linear, group variables on one side, group constants on the other side. So subtract 13 from both sides. And subtract 10x from both sides. So negative 17x is greater than or equal to negative 17. Is that okay? So in order to solve for x, divide both sides by negative 17. So what's going to happen? Yeah. Less than or equal to 1. Is that okay? Now, some students, and this is totally fine, and this is kind of, you want to do that when solving regular equations. You can predict that the sign in front of the x would be negative if you move it to the left, if you subtract 10x. Some students just like add 7x to the other side. You'll get the same answer, and you don't have to remember to flip the inequality. Does that make sense what I just said? Because look, if instead of moving everything, moving 10x to the left, move 7x to the right, then this side will be 17x, and you add 4 to that side, you get 17. See what I did? And then if you divide both sides by 17, you get 1 is greater than or equal to x, which is equivalent to that statement, right? They're the same. In this case, I didn't have to flip the inequality, because I kept my x positive. I flipped the inequality by moving it to the other side of the inequality. But anyways, either way is fine. So the solution, all x's such that x is less than or equal to 1, or everything from negative infinity to 1, including 1, or if you're asked to graph this thing up to 1, everything to the left of that. Is that fair? Any questions? Okay, sorry. How about this example? Minus 2 less than 2x plus 1 less than 5. So this is what we call a compound inequality. There are two inequalities in one. So you do the same thing, right? You want to get, the goal is to get x by itself. So we just subtract 1 all the way across. So it's negative 3 less than 2x less than 4. 3 places. And then what do you need to do to get x by itself in the middle? Yeah, divide by 2. So divide by 2 all the way across. Since we didn't multiply or divide by negative numbers, all the signs remain the same. So the solution is everything between negative 3/2 and positive 2, not included. Right? So we can say all x's between negative 3/2, x, and 2, or between negative 3/2 and 2, or if you ask to graph it, it's just going to be like this, between negative 3/2 and 2, everything in between. Any questions here? You doing okay with that? Right. Okay, good. Well, that makes me feel good. You're good. I have one more. So I have 3x minus 1 is less than negative 5, or 3x minus 1 is greater than positive 5. So that's another form of a compound inequality. There are two separate ones. We have, first of all, we have to keep in mind that magical word in between, that or. What does or mean? Yes, okay, so well, what do you mean by both? What? So what am I talking about? Am I talking about union or intersection when you say or? Is that a union, everything together, or is it intersection, the overlap? Look it up. Should be in your notes somewhere. Union, or intersection. No. Union. Or is union and is intersection. So that, the thing that glues sets together. So anyways, the rest should be pretty straightforward. We're just going to, add 1 to both sides, so x is less than -4/3. Is that okay? And at the same time, or is 3x is greater than 6 if you add 1 to both sides. So then x is greater than 2. Okay? So it's everything to the left of -4/3 or everything to the right of +2. So actually graph it first. If this is -4/3, so everything to the left of that, or if this is +2, everything to the right of that. So there are two sets that are not connected, but we need both of them, so that's where the union comes in. So in the interval notation, we can say it's from -infinity to -4/3, union from 2 to infinity. Is that okay? So that would be the graph. This is the interval notation. And this is the set notation. Which is all x is such that x is less than -4/3 or x is greater than 2. So we can use word or to represent the union. That's the whole idea. That's or. Okay? So that's it. That's the end of chapter 1. What? I don't know what you're saying. Yeah, you did. Oh, sick. No, it's not sick. It hasn't gotten sick yet. We'll get there. So